Okay, I had said there were three forces that I wanted to review with you. Three forces that we used a lot in grade 11 physics, and I need to make sure you remember them in grade 12 physics. We already talked about the gravitational force, Fg. Remember, all forces are a capital F with a subscript. Gravitational force is also called the force of gravity, and it's also called the weight. Okay? And we know from grade 11 and from what we reviewed in class that for now, until we get to planets, we will use Fg is equal to mg, where this little g at or near the surface of the Earth is equal to 9.81 meters per second squared for us. Moving away from the surface of the Earth, moving on to another planet, onto the moon, there's still a value for g. It's just not going to be 9.81. It will change. Okay, so this is known as the acceleration due to gravity, or it's also called the gravitational field strength. And the field is the area around the Earth that as long as you're in that area, you're going to feel a force on an object. And those of you in Science 12.2, you've heard that before. Okay, so that's the gravitational force. The second force is our good friend, good buddy, the normal force. Last year in grade 11, when you were learning about the normal force, and it's a capital F with an N, I asked you what the word normal meant. I know, rough crowd asked that too. But the word normal in math and in physics means perpendicular. Perpendicular to. So this force is always perpendicular to the surfaces in contact. So if I have a box sitting on the flat surface, if you could imagine that's flat, then the normal force, so the gravity always acts down. Wait, I'll tilt the paper and then it'll look flat. Gravity always acts down because towards the center of the Earth, and the normal force always acts perpendicular to the surfaces. In some cases then, Fn will equal Fg, but not always, because sometimes it's a toboggan that you're pulling. So Fg will act down, Fn will act up, but sometimes there's another force pulling up. And so there's a component of that force acting upward that's taking some of the weight off the ground. So in this particular case, if you did the sum of the forces in the y direction and it's not moving, so the MAY would go to 0, you would end up discovering Fn minus Fg equals 0. So Fn equals Fg. But here, when we do sum of the forces in the y direction and the toboggan's not moving in the y, it will be Fn going up plus the Fy going up minus the Fg is equal to 0. So now the Fn will equal Fg minus the Fy. Its Fn will be less because you're pulling upward on a rope, you're taking some of the weight off the surface. So please don't tell me that normal force is always equal to the weight. It isn't. Even when it's on a level surface. Of course, this year, they won't always be on a level surface. They will be on inclined planes. And when they are, the Fg will still act straight down, because that's what Fg does. But the normal force always has to act perpendicular to the surfaces in contact, so it will no longer be in line with Fg. Okay? Another example is, remember we held the book against the wall? And I pushed in with some force, and the wall pushed back out. And that was the second surface pushing back on the first one, which is the definition of the normal force. And meanwhile, gravity's acting this way. So Fn is certainly not equal to Fg here. The force that's acting up will be friction. And when we did this, what we discovered was that the less you pushed with, then the smaller the normal force, and the more likely the book would slide. So somehow the normal force is connected to friction. The bigger the normal force, the bigger the friction, and then it can balance out gravity. And that leads us to our next equation and our next force, which is friction. Okay, so number 3 is friction. And hopefully you remember the fun equation. So friction is capital F, Fr, and hopefully remember that friction is equal to mu Fn, where the mu is called the coefficient of friction. And it is dependent upon the surfaces in contact. If the surfaces are really rough, the coefficient will be big. If the surfaces are smooth, the coefficient will be tiny. So the size of the coefficient tells us about the nature of the surface. There are no units on the coefficient because friction is a force and Fn is a force, and so there must be no units on the coefficient for it to work out. And remember, this is our fun equation, because in non-high school physics, friction is usually written as a script F, and the normal force is usually written as a capital N. And so when you do that, you get fun. Okay? Now, just a couple of points about friction. There are actually 3 different types. There's static friction, there's kinetic friction, and there's fluid friction. And I'm going to talk a little bit about each one. Static, if you remember, is the friction between 2 objects at rest with respect to each other. So it might be a box of your grandmother's fine china on the back of a truck, and then you're driving the truck across the river. You want the box to stay at rest with respect to the back of the truck, even though the 2 of them are moving across the river. So static friction is the friction between 2 objects at rest with respect to each other. If you remember, its coefficient, and therefore its static friction itself, is always bigger than the coefficient for kinetic friction on the same surface. That means it takes more force to get an object moving than it does to keep it moving, which makes sense. And that goes back to the bonds that the surfaces form between each other when they're sitting on top of each other, right? Like, so when they're sitting there, the little molecules on the 2 surfaces that are touching kind of get to know each other well, they like each other, and now you want to move it, so you put a force on it, and the surfaces are like, no, don't go, please don't go. And you have to break those temporary bonds to get it to move. Whereas in kinetic friction, because it's already moving across the surface, it doesn't have time to form those bonds, so it's easier to keep it going. The other important thing about static friction is that it varies up to a maximum value. Okay? It varies up to a maximum value. It's not always the same value. What you find with the mu is the maximum value. I have a tickle in my throat. So this equation for friction works for static. Moving on to kinetic, this equation for friction also works for kinetic. Kinetic friction is the friction between 2 objects that are moving with respect to each other. So the puck sliding across the ice, your car going across the road, the objects are moving with respect to each other. So there's a different value for the coefficient of kinetic friction than static friction, because the static's always bigger, the kinetic is always smaller. In truth, there are actually different types of kinetic friction. There's sliding and there's rolling, and when you get to university, you'll separate them out. Here, I just want to say that the rolling friction is the smallest of the kinetic friction. So there's less friction when a tire is rolling across the ground than when it's sliding, okay? When it's rolling, there's very little friction acting against the tire. There'd be friction acting on the sides, right? So the tire's moving this way. There's very little friction acting against it. The friction would be acting like into the page to try to prevent it from sliding going around a turn. Okay, so this friction also obeys the equation FFR equals mu Fn. It's just that the mu's would be different. All right. The third type, though, fluid friction, does not obey the equation FFR equals mu Fn. Because kinetic friction doesn't depend on surface area, doesn't depend on speed. Fluid friction does, right? If you put your hand out the window, you can feel the fluid friction. If you put it this way or you put it this way out the window, you'll feel a different amount. If you put it out the window going 20 kilometers per hour or out the window going 120 kilometers per hour, you'll definitely experience a different amount of fluid friction. Okay, so fluid friction depends on surface area and contact. It depends upon the speed of the object, depends upon the shape of